Hello, everybody. It's Andrew Glasgow-Jones here, Teledyne ETV Semiconductors. I just want to check with my colleague. Can you hear me? Oh, that's great. Okay, and I think everybody who's connected that I'm in contact with can see the screen as well. So welcome to everybody for this brief presentation on deterministic synchronization of multi-element arrays. As you can see from the slide there, we are using this as part of our virtual booth at the IEEE 2020 radar conference that was to be in Florence, in Italy. So we're all very disappointed that we can't be in Florence at the moment. But we have the virtual booth and the conference is going ahead virtually as well. And so we decided to open up some interesting webinars during the coffee breaks. So the attendees for the conference are able to log in and listen to what we have to say on a number of subjects. And the subject today is deterministic synchronization of multi-element arrays. If you can see on the page there, I'm the top right, Andrew Glasgow-Jones, Field Application Engineer. I work with Julian Koshar in Europe and India. We know that this, we've opened up this webex to not just the delegates for the IEEE conference, and so we know that there are people from around the world watching. And Mark Stackler is our contact in Asia-Pac. And that's for the people in Asia-Pac who are just kind of finishing their day. We will be running the same session later on this afternoon in the second coffee break of the day for the conference. But it will be my colleague, the business development manager in the US, Kurt Rental, who will be covering the subject then. Now, in the middle there, there's two very important guys. Now, these are the applications engineers for data converters, and they've helped a lot with this presentation. Roman Pilar is our data converter application engineer, and for the interfacing and all those aspects about the deterministic latency is Stefan Bress as well. So that's a quick introduction of what we're doing and what is planned in the next day. One other thing is that we've got the same program tomorrow, but with a different subject. So we're going to be talking at the same times on direct Ka band conversion. So I'll highlight that again at the end of the presentation. So very, very quickly now about Teledyne ETV Semiconductors. We provide components for high reliability systems, and these range from power GaN, switching HEMTs, power GaN FETs. FETs isn't quite the right word, but HEMT is the correct word. And these are used in the space industry and defense, and also in the avionics industry. We have a range of space RF products. So these are products going up to 60 gigahertz, RF switches, DSAs, PLLs as well. These are available ceramic or COTS packages for space applications. We also have a range of processor products based on a long-term partnership with NXP. And we provide these very powerful processors for applications in the space market, in the defense market, and also in the avionics market. And then the main subject of this presentation is our data converters. For those of you who don't know Teledyne ETV semiconductor data converter products, we are generally in the gigasample per second ADC and DAC sample rate. We have a very good footprint in the space arena. We are also very, very strong in defense, and we also have quite a few applications in the industrial area as well. particularly telecoms and in many cases radar as well. So that's a very, very appropriate conference for us to be at. We're generally at this conference most years, and it provides very good discussion points when we're able to be on the stand. So I'll have a quick outline of what we're going to speak about. Why is synchronization important? Then we'll discuss our product, the EV12AQ600. That's a quad 1.6 gigasample per second 12-bit A to D, and the features that are included in that product, which enable robust multi-element synchronization and deterministic latency. And then we'll have a wrap up with some of the information that's available to people on the web. So here's an overview slide to describe the phased array principles that we're trying to help customers design more efficient systems based around this. I'm sure that most of the experts who are watching from the radar conference, the 2020 radar conference, will know about this very well. What we see here is a phased array. It's an array of antenna elements, and the reception or transmission of the signal to each antenna element can be delayed in phase and also adjusted in amplitude. This works in, as I said, transmission and in reception, and it gives the ability to change the energy of the antenna and enables it to be directed. So this means that the beam profile can be adjusted electronically, no mechanical parts, very quickly. So you can have scan rates much quicker than a mechanical system. You can also adjust that antenna pattern to take into account interference sources, jamming sources, those kind of effects. And so we are seeing many more applications in the fields of, certainly in the field of radar and in the field of telecommunications as well, that are using this kind of principle. Up to now, we have seen more beamforming networks that use an analog approach. You can see this on the slide on the left here. In this case, I'm looking at a receive system at the moment. The antenna signal will be boosted, then there'll be a variable gain or attenuation to the signal, then a phase, and then all the antenna elements would be summed together and then digitized by an ADC. And this gives the effect that you saw on the previous slide. You can provide a flexible beam pattern depending on the parameters that you send to the phase shifter, the attenuation and the phase part of this analog system. And there are chips that are available, core chips that perform these features in a very, very compact, way. And this gives advantages of lower power. It's a cost-effective way of forming beams, but per setting that you have in your analog array, you only have one beam. So that is good, but can be improved. And a way to improve it is to use a digital beamforming network. And in this case, all the phase and gain adjustment is done in the digital domain, either in an FPGA or a high performance processor. And using this method, you can produce multiple independent beams. And that means that the generation of that beam, or the changing of that beam, can be adapted to circumstances like jamming patterns and other forms of interference very, very adaptively in real time. Another ability that the digital processing, digital beamforming network gives you is that beam squint can be avoided, and this is the change in beam profile with frequency. So you can adjust for that digitally as part of a digital processing network. However, if this is done, it does require an accurate synchronization of those elements coming out of the ADC. Because if all those ADCs are not sampling at the same time, this provides an error in the calibration and in the calculations that are performed in the digital processing system. And so having an array that is synchronized, perfectly synchronized, is something that is very much needed for these types of systems. In addition, an efficient interface is required. Certainly if you've got lots and lots of elements in the system, you don't really have the opportunity to cable all those elements using a very wide LVDS type interface. And so an efficient serial interface is also a prerequisite for this kind of system. So as a summary for this slide, without accurate and repeatable synchronization of each ADC in the array, the digital processing will not be able to reliably form the beam patterns. Now, so this brings me to our ADC. It's a broadband quad 12-bit 1.6 gigasample per second ADC. It's got a very wide analog input bandwidth, 6.4 gigahertz analog input bandwidth, and it's also able to be interleaved. It's very flexible, so that you could have 4 channels at 1.6 gigasamples per second. You can interleave 2 of the ADCs inside the device and get effectively a 2-channel system at 3.2 gigasamples per second. Or you could interleave all 4 and you get a 1-channel ADC at 6.4 gigasamples per second. And this is thanks to the internal timing of sample point adjust, and also a very high performance input cross-point switch that enables the signal to be, the input signals to be distributed within the chip to each of the cores. It's the only 4-channel space qualified ADC in the gigasample per second range that's available. And another interesting feature of this part is the efficient serial interface. This is a serial interface that uses per core 2 lanes running at 12.8 gigabits per second. This interface is license-free. It's an open standard. You can download the source code from the website, www.easystream.com, and the VHDL code is provided. One of the features of this serial interface is that it's much less complex than other serial interfaces such as JETSI 204 that are available on the market. And so you get a much reduced FPGA resource usage. You can come down, depending on the size of the FPGA, you can come down by 50% on the number of LUTs that are required and the amount of memory that's required. So that's a big advantage for systems that need lots of channels and need lots of internal resource on the to be able to interface to the ADC. The other interesting thing is it's got a low latency. It's not a high latency interface. And I'll speak about that and deterministic latency in the next couple of slides. For the ADC, it's been designed for space applications, but also available in an industrial and commercial screening flow. Input frequency bands, as I say, go up to above 6 gigahertz. So you can do a direct down conversion up to those kind of frequencies. And I'll speak in the next slide about the synchronization chaining scheme, which means that it's easy to synchronize for the kind of phased array systems that we've been speaking about. I think that's covered most of the points on this slide, so I'll go to the next slide. Here on the left, you can see a typical phased array system with 16 elements to the antenna. Already, this is showing that the AQ600 can be used to interface a 16-element antenna to a mid-range FPGA. So that's already an interesting feature. There's no need for multiple FPGAs for 16 elements. And there's also no need to double the number of ADCs that you require. For example, a two-channel ADC would need double the number of ADCs, so that doubles your board area and doubles your cost as well. The synchronization feature that we've added uses a signal that is passed as a daisy chain from one ADC to the next ADC. Up to now, synchronization signals have needed to be fanned out using a fan-out buffer that increases requires another component on the board, and so increases your requirement for board area, increases the power supply requirements, and it also needed the design of this to be done very, very carefully, because the routing of this and the skew calculations that were needed to be put in were quite exacting, and they added another level of complexity to a board design. And so this feature, we wanted, with this feature, we wanted to provide a method to avoid that. And so what we have is a signal that is passed from ADC to ADC. There's a one-time training that sets up all the timing parameters. So there's some internal timing parameters in the ADC, some timing parameters in the EasyStream interface. And for a one-time board or system level setup, this enables these parameters to be measured, stored in non-volatile memory, and then every time that the system is powered up from then on, the ADCs, or the data coming into the FPGA, out of the interface of the FPGA in the FPGA, will be fully synchronized. We've produced a video. It's available on YouTube, and this shows an example of how we've got two ADCs synchronized together. Here's the sync chain. It's using a cable. That's another feature that is interesting, and we've got a number of customers using this, is that in that the sync signal doesn't automatically need to be a PCB track. It can be also a cable that's passed over the back plane or a front panel signal as well. And here's the system prior to this training sequence. The two cores don't have the data coming out at the same time, and the delay between them is down to this cable that goes between one ADC and the next ADC. Once the training procedure has been performed, the data is perfectly aligned and synchronized. And you'll see on the video that we did quite a lot of measurements of the robustness of this synchronization feature, in that we heated up ADCs, we took off a heat sink from some ADCs, we removed the clock to ADCs, we power cycled, and every time the synchronization feature came up and saw the data coming out as perfectly aligned. So this is the EB12AQ600. It has the multi-ADC synchronizing function with the efficient serial interface. And also there's in 4-channel and 2-channel mode, there's a sample point adjust feature that enables these possibilities to be calibrated as well, the incoming signal to be calibrated from the antenna. In terms of deterministic latency, now many users don't so much need a short latency, but they need to have a deterministic latency, because if every time the system is power cycled, each element of the system comes up with a different latency, and that latency also has a jitter on it, then that will have an impact on any calculation the digital beamforming network can do, and will require ways around this. Easy Stream and the easy synchronization feature allows a robust and repeatable deterministic latency without the need for external fan-out components that you get with existing systems using LVDS interface, and also JESI 204, which requires an additional fan-out for the sysref function as well. In terms of overall latency, our ADCs have an architecture that has a very short latency, and it's one of the additional features of Easy Stream that even by adding a serial interface onto that ADC, we don't impact on the latency too much in terms of a serial interface. So the Easy Stream and AQ600 overall latency is significantly better than any other serial interfaces that you can see on the market. And so this has also an effect on a potential application in electronic warfare systems, where you need either to react quickly or to follow a frequency that's hopping quickly as well. So as kind of a summary slide here, you can, using AQ600, you can go from an analog beamforming system to a digital beamforming system with all the advantages of multiple independent beams, improved beam shape, fast response, adaptive array processing. We have the features here for the multi-ADC synchronizing function, efficient serial interface, sample point delay in 4-channel and 2-channel modes. A bit of a update here on our next generation DAC as well. This will be a dual 12-bit, 12 gigasample per second DAC with greater than 20 gigahertz bandwidth and extensive digital features. This also has the same sync procedure. So the ability to synchronize multi-elements in a transmit application will also be available with the DD700. As far as the AQ600 goes, evaluation boards are available. We have a single ADC board that was produced by SB Devices, We have a dual ADC board that was produced by the Fraunhofer Institute, and that is particularly useful for demonstrating synchronization of two ADCs. And we will also be producing an FMC board. That's due for later on this year. And here's some useful links. There's a product webpage, datasheet, download from the EasyStream website, the YouTube video on synchronization, and technical queries on the interface to Stefan Bress, who's based here at the factory in Grenoble. So this is the final page. I've gone over the coffee break by 5 minutes, so sorry about that. Just a reminder that we'll be going through the same presentation between 1640 and 1700 this afternoon. It won't be me that will be doing the presentation, so if you want to listen to this thing again with a slightly different take, it might be my colleague Kurt Rental, who will go through it. So yeah, he'll be doing it in an American accent rather than the British accent. And also don't forget that we've got a presentation same time tomorrow, 10:40, on direct KA band conversion systems. So thank you very much, and have a good day and a good rest of the conference.